Okay, welcome back everybody. So we are on lecture 4 now in Intro to Physical Oceanography. And I mentioned I made a post on Brightspace, so now at this point all of the lectures should be getting uploaded to YouTube. For the first 3, I actually didn't realize it was saving it in like selfie mode or something, so everything is mirrored left to right. But I think I fixed that. So the future lectures should be somewhat visible, although really you only get an okay view of the slides from the videos anyway. It's more about having the verbal explanation, and all the slides are posted on Brightspace. So I would suggest use some kind of combination of the two, maybe listen to the explanation while you look at the slides or whatever. Okay, any questions before we get started? Any questions about the assignment, anything like that? Okay. All right, so as always, we do a little bit of review. So last time we sort of concluded our talk about the geography of the world oceans. We sort of talked about first where the oceans come from in terms of the formation of the solar system, formation of the atmosphere, ocean, and Earth. And we talked also about what controls the configurations of where the continents actually are. And of course, the ocean basins are between the continents, so continental drift kind of determines the shape and arrangement of the ocean basins. And we discussed this idea of continental drift, that we used to have Pangaea, one large continent, where sort of all the continents were sort of smashed together with this big sea around it. And there was all sorts of evidence for that, that prompted us to talk a little bit about global climate change and the ice-albedo feedback. So this is the idea that if you have a top of the atmosphere perturbation, so what that means is there's maybe more radiation coming in at the top of the atmosphere, or there's less coming in, so some kind of change, that there are certain pieces of physics in the climate system that can either amplify that change, like make it larger, or it can mute that change and make it less effective. So, and the ice-albedo feedback is an example of one of these things they're called climate feedbacks that actually amplifies changes. And the way it works is, you might imagine that, let's say due to Milankovitch forcing, so some sort of changes in the orbit, we get a little bit less sunlight coming in at the top of the atmosphere. So less energy coming in means the climate's going to cool. When the climate cools, that means you tend to grow more ice. So, not infinitely more ice, but incrementally more. That extra addition of ice reflects away more solar radiation, which leads to even less radiation coming in, so leading us to cool more. So it's like a little amplifier that can cause perturbations of the climate to have a larger effect than they otherwise would. And there's all sorts of climate feedbacks like this. You can take whole courses on them. And there's many, many different examples. But the ice-albedo feedback is one of the most important ones at the global level. And you'll talk about that on the first assignment. So that was sort of a small part of the discussion. But then we were also talking about evidence for plate tectonics and this movement of the continents. And then this picture was pretty important. So this is this idea that the way the ocean basins are structured is that, so the sea floor is oceanic crust, and so this is mostly basalts and sort of denser materials on the bottom of the ocean. And this new, an ocean crust is actually formed in the center of the ocean basins at these places called mid-ocean ridges, where hot material from the upper mantle comes to the surface, becomes magma at the very top, and it forms new ocean crust. And then that ocean crust over tens of millions of years sort of moves like almost on a conveyor belt, driven by these circulations in the mantle and other forces as well, such as the gravitational pull on the plates. And over hundreds of millions of years, or at least tens of millions, it moves, the pieces of crust move from the mid-ocean ridges to the edges of the basins, where they meet these trenches, these very, very deep trenches in the ocean floor. And those are called subduction zones, and that's where the oceanic plates they subduct beneath the continental plates, for example, on this side. And so actually over hundreds of millions of years, the entire sea floor is actually recycled. And you can see this from this image on the bottom right, which is the age of the sea floor. You have very, very young sea floor, only 1 or 2 million years at the mid-ocean ridges in the Atlantic and the Pacific, for example. And as you get out to the edge of the basins where the trenches are found, you get the oldest ocean floor, which is about 200 million years old. Yes?
Are those ridges responsible for the continental drift? Because continental drift, like, all those continents were together at one point, they have to be separated due to continental drift. are these ridges responsible for that? Because I believe it would be a lot harder to pump out material to the surface if there's.
Yes. So actually, so that's a very, very interesting physical question. So that gets to that's a question that's in the area of what's called solid Earth geophysics. And fundamental question is what's actually causing this seafloor spreading? What's actually causing the movement of the continents? And that was debated for many years. I think it continues to be debated actually, because it's quite difficult. You might want to answer a question like that. You might want to do something like consider the forces involved, estimate the forces. If you know the forces, could you actually estimate a drift rate? Could you predict which ways the plates are going to move based on those force considerations? But it's quite difficult without direct observations to actually measure those things. And so there actually was, in solid Earth geophysics, there was a debate over many years called ridge push. So this is the mid-ocean ridge. And one idea is that the ridges, as you form new crust here, that it's pushing the seafloor away. So ridge push would be one effect. And then trench pull is the other idea, that as these slabs fall down, these are cold and dense, and they kind of get pulled down by gravity and sort of pull the slab into the interior. And then there's also things called tractions, and these are basically, you can see this, so if you have convection or some sort of circulation going on in the upper mantle, the fact that the mantle is moving this way can sort of pull the surface along with it. And so there are stresses or forces on the bottoms of the plates that are due to mantle convection. There are push forces that are coming from the mid-ocean ridges, and then there's trench pull or slab pull happening at the edges. This is not my actual area, so I'm not a solid Earth geophysicist, so I'm aware of these debates. I don't actually know exactly how it is settled, but I think exactly the nature of the forces that cause these things, I don't know if it's completely understood. We have computer models that help us try to understand it, but that's a very important question that's been debated for quite a bit of time. I would say all of those effects play a role. Exactly which one is the dominant effect, I think it's an open question maybe. Yeah, solid Earth geophysics would be where to look. Very good question. Okay, so this age of the ocean floor, basically just looking at this picture, you can almost infer the idea of plate tectonics. Okay, so that's sort of all we're going to do in terms of the geology and the geography of the ocean basins. And so then we moved on to water. So we're going to study, obviously, water and the properties of water have a big impact on the ocean circulation and the climate in general. And we started off very basic about just the molecular structure of water. It's polar, it has hydrogen bonds, and then this led us to discussions of the thermal properties like the heat capacity. So today, we're going to continue that discussion of sort of the thermal properties of water, and that's going to lead us to the cycles of evaporation and precipitation, which I think is the last topic on the assignment that you need, understanding evaporation and precipitation. And then towards the end, we'll talk about what are the physical factors that affect the density of water, which is very, very important for things like buoyancy and convection. And then on to salinity, which will be a sort of a theme that comes back throughout the course. Okay, so last time we finished on this slide, which is just saying that if you compare a substance like water, so it's 3 atoms in this interesting bent shape involving hydrogen bonds, and you compare the melting point and the boiling point of water, they're much, much higher than something like carbon dioxide, which in some sense is similar. And that's because water likes to stick together because of its hydrogen bonds and van der Waals forces. And it also has a very high heat capacity, meaning you can add a lot of energy to water without raising the temperature very much. It basically means that water is very, very effective at holding heat. And this is one of the reasons why people often talk about like maritime climates or ocean climates. So Newfoundland has a sort of a milder climate than, say, Toronto. Toronto has very, very hot summers and very, very cold winters, whereas we might get a lot of snow and rain and stuff, but our actual temperature is relatively even compared to other places in Canada. And that's because the ocean has this big heat capacity. It sort of changes slowly in temperature because it's so good at absorbing energy. And so this has to do with the fundamental molecular properties of water. So a particular thermal property that's very, very important in climate is this property called latent heat. And so the heat capacity of water or any substance tells you, as I add heat to that substance, how much does the how much does the temperature change? Latent heat is very similar, but it says as that substance or material changes phases, so it goes from solid to liquid or liquid to gas, how much energy is involved in those phase transitions? And so to sort of understand how that works for water, there's a nice diagram, this is from the book, that sort of explores what are the energetics involved as we take, let's say, a sample of ice. So ice at some sub-zero temperature, maybe I think we're starting at minus 20 degrees or minus 40. And as we add energy to that, where does the energy go, and then how does the material change? And so what this plot is showing is the x-axis is energy. So you can think of this, it's written in calories because the book is American, but you can think of it as joules, any kind of unit of energy. And then the y-axis is the temperature of the sample. So it's going to start off as ice at minus 40, and then we're going to end up putting it up to 140 degrees Celsius in the form of steam. And so what we're going to imagine doing is taking our cold sample of ice and then adding more and more joules of energy, and then looking at what happens to that substance as we do it. So all the way on the left-hand side, we're going to drag this box across and highlight the different parts of the graph. So on the left-hand side, you see there's a straight line. So as we add energy, about 20 calories or whatever of energy, the temperature starts going up linearly. So for each joule we add, or each calorie, the temperature goes up a constant amount or a steady amount. And then the slope of this line is related to the heat capacity of ice. So we start adding energy, and then the ice goes from being minus 40, warming up until we get ice at 0 degrees. And as we all know, at 0 degrees, the ice is going to start to melt. And it turns out that what happens is, as we add energy to the ice, when the ice is at 0 degrees, so it's going to change from being solid ice to liquid water, the temperature stops changing. Because when we add energy, instead of going into warming the substance up, it goes into breaking the bonds that make it a solid, separating out the molecules and turning it into a liquid instead. So there's this period where we're adding energy and the temperature's not going up. So we're adding energy, but the temperature's staying flat because we're breaking the intermolecular bonds and transforming the substance from a solid to a liquid. And the amount of energy we have to add in, and it's measured per gram of the amount of ice we have, is called the latent heat of melting. And just like all the other thermal properties of water, it's relatively large for water compared to other substances. And 80 calories per gram, the numbers, if you want SI numbers, I'll always give them on the assignments. So we add energy, and then we break up the intermolecular bonds and go from ice to water. So then we continue adding energy, and now we get it again into one of these linear straight line phases, where we're now taking our sample of water, which was originally at 0 degrees. We're adding 100 calories of energy, and that takes the water from 0 degrees up to 100 degrees. And again, we have this linear straight line. So as we add incrementally more energy, the temperature just goes up proportionally to how much we added. Until we get up to 100 degrees, and now we have another one of these latent heat phases, where again, so now we're continuing to add heat now to our sample of water, but instead of that heat going into increased temperature, it goes into breaking up those intermolecular bonds and taking that liquid water and transforming it into water vapor or steam. And something that's very important, and this is very important in the climate system, I'll explain now in a few slides just why it plays such a big role, is that this horizontal plateau here is very, very wide, which means that to go from liquid water to steam, you have to add a huge amount of energy. It's 540 calories per gram. And as I'll explain shortly, you can think of all that energy that you put in as being stored in the water vapor. And because energy is never created or destroyed, it's just turned into different forms, that energy can later be released, and it has a major, major effect on the atmosphere. And we're going to talk about hurricanes later. It's almost the fundamental thing that drives hurricanes. So the fact that this number is really big means that water vapor stores this huge amount of energy when you've evaporated it and made it into water vapor or steam. And then you can continue. As you heat up the steam, you add more energy. This slope would be the heat capacity of water vapor. And so we end up with this sample of steam at 150 degrees or so. So we go from all through the different states of matter, but the important thing is that every time we transition, there's a latent heat involved where you don't increase the temperature, you just break apart the bonds. So the whole process can run in reverse, and you go from steam to liquid water back down to ice. And a very important part of this process is that when you want to melt ice or you want to evaporate water, you have to put energy in. You have to boil the kettle to transform it from solid to liquid and then liquid to gas. And when you go in the reverse direction, all that energy is released back out. And so in this process, especially when you go from water vapor to liquid water, and this happens, for example, in precipitation, condensation, and clouds, all of this latent heat that was stored gets released back into the atmosphere. So when we go in reverse, steam, water, ice, the energy gets released. And you can imagine that we all know sort of, we'll talk about this in more detail, but like warm air rises, for example, right? So when you release that heat into the air, it's going to warm the air and it's going to cause ascending motion. So we actually get stronger, like say, more vigorous updrafts, more vigorous thunderstorms because of this huge amount of latent heat that gets dumped into the atmosphere when water condenses from vapor form into the solid form. Okay, so to sort of get a physical picture of how this whole thing works, I think it's worthwhile to think about what happens with evaporation and condensation at a molecular level. So here I've just drawn a little sketch, and you can imagine, so this is the sea surface, so we've got a little wave, and we're just going to look at, imagine a little box, little cube of water that's just at the sea surface, and so maybe some of that water is going to evaporate and become water vapor. So if you zoom in, so I've sort of popped it out here, this box is full of water molecules, but the molecules, they don't all move at the same speed. So actually they sort of have a distribution of speed. Some are faster, some are slower. Actually physicists in, I think the 1800s started to come up with concrete ideas about exactly how many are moving fast versus how many are moving slow. This is an area called statistical mechanics. But the idea is that there's some slower molecules, I've colored them blue, and then there's some faster molecules that I've colored them red, and generally the faster ones are rare. And actually we know from theoretical physics that you could plot a distribution of the speed. So now this is sort of you can imagine like a probability plot or a bar plot. So the x-axis is how fast the molecules are going, and the y-axis is like what fraction of the molecules are going at that speed. So, and this changes depending on temperature. So the warmer the sample, the more energetic the velocities. So if you look at how many molecules are totally stopped, no velocity, that's very, very few, or maybe zero. And then as you increase the speed, there's this peak. So there's some most common speed. So that would be like maybe these blue molecules are traveling at the most common speed. And you go, and when you look for faster and faster molecules, there's a tail here, so you get less and less and less of them. So what happens in evaporation is that you can think of it like there's all these molecules sort of bubbling around, hitting each other. And to evaporate, a water molecule has to fly off and leave the liquid state and join the vapor state, or just join the air that's above that sample. But it's pulled back because of hydrogen bonds and intermolecular forces. So it's almost like you can think of like a rocket trying to escape the Earth's gravitational pull and go into space. So you probably have seen the term escape velocity before. So to get a rocket actually to go into space, you need to have it going fast enough to escape the Earth's gravitational pull. So the same thing, pretty much, is true for evaporation. It's only the fastest molecules that are going fast enough that they can actually escape the attraction due to hydrogen bonds, van der Waals, of these other molecules, and actually escape and fly off into the atmosphere. So here we have a couple of these fastest molecules that are escaping. And so in terms of the distribution, you can sort of say, well, out on this tail where there's this fastest region, these are the ones that have velocities that are beyond the escape velocity, and so these ones can actually escape. So the next key idea is, if you think about now, imagine you have the top 1% or whatever of molecules. They escape because they got these fast velocities. Well, when they leave, they take their kinetic energy with them. And so whatever water is left is now moving relatively slower on average. And in physics, the movement and the speed of the molecules is the same thing as the temperature. So when you have these fast molecules leave, the rest of the molecules are relatively slower on average, and that's the same thing as a cooling. So the temperature has gone down. So this whole process of these molecules leave, and they leave behind a colder surface ocean than before, that's called evaporative cooling. And that's the same reason that humans sweat, because your sweat evaporates on your skin, that helps you thermoregulate. And it's the same exact principle. You lose the fastest molecules, then everything else is relatively slow. So how this works in the ocean is it's a two-step process. So on the left-hand side, this is basically the same kind of diagram that we had before. So you can imagine you have the surface ocean, and then if there's evaporation occurring, you have water molecules, and they're sort of escaping, so just drawn them up here. So water vapor is escaping the surface. That's always the fastest, most energetic molecules. And so the surface ocean is cooling evaporatively. Sorry for the handwriting. So the surface ocean has evaporative cooling, so that means the ocean surface is going to cool. Basically, energy is leaving the ocean surface, and it's getting stored in this water vapor in the atmosphere. And that tends to happen, obviously, when we have warmer oceans, because that means you have higher energetic, warmer surface temperature, that's more likely to evaporate. So we store this, we remove this energy from the surface ocean, store it in water vapor in the atmosphere. Then in part 2 of the process, the atmosphere takes all this water vapor and moves it around. And later on, in the mid-latitudes, meaning say around where Newfoundland is, what happens is you have rising air in cloud formations. You have air that rises because of various sort of fluid dynamical reasons. And then when it rises, we all know that, and we'll cover this maybe in more detail. So when you go up higher in the atmosphere, it gets colder. So like you see snow on the tops of mountains, for example. So when you have rising air, it cools. Cold air can actually hold less water. So the water comes out in the clouds. We form these clouds. And then what I've colored here in red is because when you have water vapor condensing from the vapor phase into the droplet phase that make up the clouds, all that latent heat is then released into the clouds, and the air is actually warmed, and that causes extra buoyancy and more vigorous vertical motions. And so this plays a key role in thunderstorms, hurricanes, etc., as I mentioned. And so really, evaporation and condensation and precipitation, what they represent is a very, very large, and you'll estimate on the first assignment just how large it is, energy transfer, where energy is removed from the surface ocean and dumped into the atmosphere, and it can be dumped into the atmosphere at a faraway location. And so you can sort of characterize where in the climate is the ocean giving up energy, and where is the atmosphere inheriting that energy. And this is a cartoon. I'm going to show the data now in a minute. So again, evaporation and condensation precipitation, it's basically this global energy transfer system. And you can, roughly speaking, think of it as there are these latitudes with very warm sea surface temperatures, and it tends to be, so why is it not right at the equator? I'll address actually in a minute, but it tends to be that the tropics, where they have warm sea surface temperatures, you get lots of evaporation. So the ocean is losing energy, the surface ocean is losing energy in these bands, and where that energy is going is up in these sort of mid-latitude 40 to 60 north, 40 to 60 south regions, right where we are. It gets dumped into the atmosphere in the form of clouds, you may have heard people talk about the atmospheric storm track before. We know we get lots of blizzards and vigorous rainstorms and stuff here in Newfoundland. That's in significant part due to the energy that was injected into the atmosphere in the tropics that was then brought to our location that gets released in the air. But this is a cartoon. So this is what the real data looks like. So this is showing the patterns of global evaporation. So we can see higher, sort of redder or more yellow colors means more evaporation. And so all along the sort of tropical bands, around 30, you especially have 30 north and 30 south, you have enhanced evaporation. And then once you get into the mid-latitudes, there's very, very little because the sea surface is just colder. You also have less direct sunlight. Direct sunlight also helps evaporation as well. And you can see some cool features on this plot. So for example, this region here, does anyone have any idea, like, what is this region and maybe why would it be more red here? Yeah?
The Gulf Stream.
Gulf Stream, that's exactly right. So why would it be more red, do you think?
A lot of warm air comes up, I guess it gets brought up around that area and then cools up. I don't know.
So warm air, and also the fact that the water is warm also. So the Gulf Stream's a warm current, so it has to do with the atmospheric processes as well. But a major factor is that this Gulf Stream brings up, and we'll talk about the Gulf Stream in a lot of detail, the Gulf Stream brings up warm water from the tropics all along the eastern seaboard here. And so you have warm sea surface temperatures, and actually you also have sort of a colder, drier atmosphere. And both of those, the air being dry also sort of facilitates evaporation. So you have major evaporation here. How about, does anyone know what this area is? Has anyone ever heard of the Kuroshio current? Okay, so in eastern U.S. and Canada, we have the Gulf Stream, and the Gulf Stream is this very strong warm current that happens on the western side of the Atlantic. So here's the Atlantic, eastern Atlantic, western Atlantic. On the western side, that's the Gulf Stream. The same thing actually happens in the Pacific, but hardly anyone knows about it until you take oceanography. But so here's Japan, and here's the Pacific. On the eastern Pacific, that side, and on the western Pacific, you have a very similar current. It's kind of like the Pacific analog of the Gulf Stream, and it's called the Kuroshio, and it runs up through Japan. So in Japan, they don't know the Gulf Stream so much, they know the Kuroshio, and here it's the opposite. And if you study oceanography, you get to have the global view, which is why you're also lucky. Okay, so a interesting feature is that generally, the Earth, the equator is where we get the most sunlight, the equator is the warmest. So it's a bit strange that right along the equator, there's some blue here. There's like the main regions where the evaporation is the strongest are in the tropics, but not actually right along the equator. And and the reason for that, this is just another version of a very simple plot. This is now showing evaporation and precipitation. So red means lots of evaporation, and blue now is including not just condensation, but actually precipitation as well. And what we see is right along the equator, there's this really, really dark blue band, and that means you get lots and lots of rain there. And there's a special name for this region. It's called the Intertropical Convergence Zone, or ITCZ. And you can actually see this from space. So if you look at a satellite image, so here's, this is the Gulf of Mexico here, Cuba. And so if you look at the equator, and this is true on average, maybe not at every moment, but in general it's statistically true, that if you look at the equatorial band all around the Earth, you see lots of enhanced clouds there. And we'll talk about exactly why that's happening, but basically, because we have a very cloudy atmosphere, you have less sun getting in. Sun facilitates evaporation. So right at the equator, you have a little bit less evaporation than you otherwise would because of this intertropical convergence zone, which is really important for the climate and appears as this very obvious band of clouds that sort of circulates all the way around the planet. Okay. So, as I mentioned, so on the first assignment, you will get a chance to look at some numbers related to the rate of evaporation and precipitation and just how much energy is involved. It's a very, very large amount of energy. I was very surprised when I first did the calculation. But now we're going to move on to not just the thermodynamic properties of water, like the latent heats and so forth, but it's direct physical properties. So, for example, the density, we're going to sort of tie this into salinity. So, we all probably know from chemistry, high school chemistry or high school physics. So, density is basically how heavy something is for its volume. So, it's defined as mass over volume. You take a cube of water, you weigh it, you take the volume, the ratio is the density. We use the Greek letter rho almost always to represent the density. And for essentially all substances, all materials, water, metals, whatever, air, the density of that material depends on its other properties. So for example, it depends on how hot or cold it is, depends on the temperature. We'll also see that the density of water depends on the salinity. And a very classic equation that tells us about the density is the ideal gas law. So here I've written, this is a slightly different form, so you might normally see the ideal gas law as maybe you've seen it written PV equals nRT. But N is the number of moles of the gas. So up to a constant, that's how much gas you have. It's kind of the mass. So what we do is we say divide both sides by V. So we get P equals N over V times RT. This part here is kind of like the density. And then if you divide both sides by RT, you get P over RT equals density. And exactly how you define the ideal gas law, there might be a molar mass in there. Those details aren't important. But this is called the meteorological form of the ideal gas law. It says that the density of an ideal gas is exactly equal to its pressure divided by gas constant and divided by the temperature. And so it kind of makes sense. As you increase the temperature, the gas expands and the density goes down. And as you increase the pressure, meaning you're sort of squeezing the gas with higher pressure, its volume decreases and the density goes up. So the ideal gas law is a very, very beautiful, simple result that applies to simple gases. And the same concept, though, applies to everything. So that there's some kind of fundamental relationship between density and then things like temperature, pressure, maybe salinity. The ideal gas law we learn in high school or first year courses. But the key thing is that we may not have a formula that's so simple for something like water. You know, you can actually, in advanced physics courses, you actually derive this formula. But even if there's not a simple formula that can be derived, the fundamental idea of that relationship still exists. And these relationships are called equations of state, or we sometimes use EOS. And so what an EOS does, it relates the density to the other properties like pressure, salinity, temperature, so salinity in the case of seawater. So we're going to now talk a little bit about what the equation of state of water looks like, so how its density depends on its other properties, and what the implications of that are. Yes?
Is the temperature Kelvin?
So yes, yeah. So in the ideal gas, the temperature is in Kelvin, and that's actually crucial because if you think about this, if this was in Celsius, right, then at 0 degrees Celsius, this would predict an infinite density, right? Because if that was a 0, then you'd have P over 0, so that gives you infinity. So T here, whenever we're doing thermodynamic calculations, you always use Kelvin. But on homeworks and stuff, you can use whatever you want. And a key thing with Kelvin versus Celsius is that Kelvin and Celsius are different scales, but they're the same if you're looking at differences in temperature. So if one object is 5 degrees Celsius warmer than another object, it's also 5 degrees Kelvin warmer. But the absolute temperatures are enormously different in the two scales. Yeah, so generally in thermodynamics, you use temperature and Kelvin. That's right. Okay, so for water, as I mentioned, it's not possible to derive a simple formula. So it just turns out gases, kind of all of the molecules are far apart. They're not really interacting that much. And it turns out you can derive the ideal gas law. It's not trivial to do, but it's not super hard. You can cover it in an undergraduate course. But for liquids, the interactions are very much more complicated. You have hydrogen bonding and van der Waals. All the molecules are very, very close to each other. So no one has ever been able to derive or prove what the equation of state looks like, what that density relationship looks like. But the relationship still exists kind of in the abstract sense, right? So there is some relationship. It's a one-to-one relationship. But it's just not a simple formula. So the way we can write that is just that the density, this is for fresh water, so we're going to say there's no salinity. So the density of fresh water is equal to some kind of function of the pressure of the water and the temperature. And so we don't know what this function is. It's some kind of relationship. Maybe you could put it into a computer program or a spreadsheet or something. But if you tell me the pressure and you tell me the temperature, using this formula, I can tell you the density. So usually, because there's no formula, you represent this stuff graphically just by plotting what it looks like. And so this is what this diagram is showing. So you can ignore the green line. The green line is some other example. But the red line is showing as a function of temperature. So we have warm temperatures on this side, and then cold temperatures going down to 0 on the left-hand side. And the red curve shows the density of fresh water. And so what we can look at is if we imagine taking a sample of fresh water at 20 degrees, and then we start cooling it down. So we're removing energy, we're cooling it down. And as you cool it down, the density increases. And so this is called thermal contraction. So as you cool something, it tends to reduce its volume, and then that causes the density to be higher. You may have seen this, the opposite of this is thermal expansion. So if you add heat, you warm something up, it expands a little bit. And if you've ever tried to get like a metallic lid off a really tight jam jar or something that people do is they run it under hot water, that causes it to expand a little bit and you can get it open more easily. So this is the opposite of that. So we're taking heat out and it's contracting, and if you put it under cold water, the lid would tighten. And so that's the normal behavior. You take heat away, and the density increases because of contraction. But water has this very, very interesting property that doesn't continue to happen all the way down to 0 degrees. Actually, there's a temperature where this red line meets a peak. So the maximum density actually occurs not near 0, the freezing point, but at 4 degrees Celsius. And this property, it's actually only true for fresh water. It's not true for salt water. We'll see that later. But it has really interesting impacts on sort of climate and on ecology especially. And so I'll just give an interesting example here. And what this really does is it just serves to show how the equation of state, how the density depends on temperature, can have an effect on circulation in sort of very important ways. So let's consider what happens to a freshwater lake in wintertime. So we imagine we have some lakes. Here's the surface of the lake, there's some fish in there, bottom of the lake, and then it's wintertime, so it's a cold atmosphere here. And so what this means is that the upper layer of the lake is going to lose energy, maybe evaporative cooling, maybe just direct contact cooling. Going to lose energy to the atmosphere. So heat escaping the upper layer, going up into the atmosphere, and so that's going to cool the surface layer of the lake and bring it down towards the freezing temperature. But because as we get below the maximum the maximum of the density, we get this opposite effect where normally when you cool water from 20 to 4 degrees, its density increases. But then when you cool it below 4 degrees, the density actually starts to decrease again. So when we're cooling this water and it's getting down towards the freezing point, we get this cold surface layer, but that cold surface layer is actually less dense and floats on top of a warmer interior. So you actually have a situation with cold water on top of warm because of this peculiar behavior of the density of water between 0 and 4 degrees. And so this cold surface layer, we sometimes call it a lens. Basically, it sits as this layer on top, and there's a warmer layer underneath. And so the first thing that's going to freeze is actually going to be this surface layer, and the interior is really protected from that cold atmosphere by this cold surface layer that's eventually going to freeze. So the next stage of the evolution here is we have our cold atmosphere, and now the surface has cooled sufficiently to actually become ice, with a cold, buoyant layer underneath it. But in the interior, we still have that warm interior. So the lakes don't freeze all the way to the bottom. And any kind of biology or whatever that lives in the lake, generally, unless you had a very, very cold, very, very long, like ice age type scenario, generally freshwater lakes, they don't freeze to the bottom because the interior of the lake is protected by this floating layer of cold water that sits on top. And this is all because of the peculiarities of the equation of state for freshwater. Okay, and I got this example from a book that was written by another member of this department, Yakov, if anyone knows him. Okay, so this is all freshwater, very interesting physics. But salt water is quite different, so we have to talk about salt. The term we use in oceanography to quantify how salty water is salinity. And salinity has this very particular definition, which basically says if you imagine you have a sample of water, so this here is 1,000 grams of water, and when I say water, I mean the salty water itself. So the water and the salt and everything else inside. The total pi is 1 kilogram. So for normal seawater, the amount of that 1 kilogram that is salt ions tends to be about 35 grams. And how we express salinity is we define this S, which is salinity, and the definition is it's the mass of the salt divided by the total mass, including both the salt and the H2O molecules. So you can think of this as total mass, but it's M salt divided by the sum of the salt plus the water, so the entire mass. And you'll have a chance, I think on the first assignment, or maybe I think it's the first assignment, to get some confidence with the details of this definition. And so we usually, because we generally have about 35 grams of salt per 1,000 grams of total sample, we measure salinity normally in parts per thousand. There's also a couple of other units that is measured in. And so a usual value you see is called 35 ppt. And they use this symbol like an O with a slash and then two O's. So if the second O wasn't there, that would be percent. But because there's two O's, that's per thousand. So instead of per 100, which is percent, it's per thousand. So a typical number to keep in mind is 35 parts per thousand. If you look in the open ocean, that's a very common number. Rivers and things, if you look at where rivers are going into the ocean, it's a lot less, for example, because we're mixing fresh water and salt water. A very interesting and important aspect of the ocean sort of chemistry is that, generally when we think of salt water, you think of sodium chloride in the water, but actually the salinity has a bunch of different components. Sodium chloride is the main component. So if we break out this 35 grams into its own pie, a bit more than half the pie is chloride ions and sodium ions. But then there's other stuff in the water, sulfate, calcium, magnesium. There's also dissolved gases like carbon dioxide. But there's all these different components, but it's relatively okay to think of it as mostly NaCl, different kinds of salts. But of course, for biology, for example, the fact that there's iron in here and potassium, those are all important for biological processes as well. So, we have 5 minutes left, so I'll raise a question. So, we all know the ocean is salty, but to do science related to that, you would want to measure it. It's precisely how salty it is. How does that vary from place to place, maybe in time? So, how could we measure ocean salinity? Does anyone have any? There's numerous ways that it's done. But does anyone have an idea? What would be one or a few ways that we could actually measure the salinity of the ocean? Any thoughts? Any one?
Conductivity.
Conductivity. That's right. So that's the way that in practice it's mostly done in essentially all practical real world oceanography applications. It's done using conductivity. So basically, how does that work? Why does that have anything to do with conductivity?
Ions are able to conduct electricity very well,
That's exactly right.
and having loose ions in seawater, which dissolved salt, for example, that's able to conduct electricity very well.
Exactly. That's exactly right. I couldn't have said it any better. So ions, when you take salt, so NaCl is electrically neutral, but when you break it in half and you take the sodium and the chloride separately, one has a plus charge and one has a minus charge. And so there's charges kind of floating around in the water, and those charges can be used to carry electrical currents. We have generally the saltier the water, the better it conducts electricity, and then by basically using some kind of calibration, you can measure the electrical conductivity and infer the salt content. But there's other ways as well. That's the mainstream way that it's actually done in practice. But there are other ways that it was done historically and for various other applications. So does anyone else have another idea? What would be another way you could measure salinity?
Just take a part of the ocean part and then boil it.
Yeah, boil it. That's the simplest way, right? That's what I would do. I mean, if I didn't sometimes I like to think, if you were transported back to like the year 1500, like how much science could you actually reproduce? And I probably couldn't reproduce the conductivity meter, but I could boil water and maybe weigh the salt against some stones with a balance or something. So you could measure it just by boiling. And so that's sort of or evaporation. So that's the classical method. You take a sample of seawater, boil it down, you got the salt left over, weigh how much you had at the beginning, weigh how much salt you have at the end. And actually, this is incredibly accurate. It's actually accurate to, even though it's sort of this ridiculously easy method, the most obvious thing you think of, it's actually accurate to about 1/100%. So not 1%, 1/100%. But because the salinity variations of the ocean are so subtle, actually that's not accurate enough, even though it's very accurate for quantitative oceanography today. That's because actually a very small amount of the salts are volatile enough that during boiling they can actually escape into the atmosphere. So other methods are more accurate. So this other method, probably no one would come up with this one, I wasn't aware of it, called the method of constant proportion. So this is very interesting. So it turns out, if you look at this pie, if you break out the total amount of salt, there's a certain amount of chloride, a certain amount of sodium, etc. And if you look around the ocean, the relative ratios of all of these different components are very, very constant. So wherever you look in the ocean, there's a different amount of total salts. But if you look at how much of the salinity is sodium versus chloride versus whatever, those ratios are pretty much fixed. And that's called the principle of constant proportions. And that happens because over millions and millions of years, the ocean is sort of stirred up very, very well, and these things get homogenized. And that happens because the time scale, or the length of time over which the ocean sort of gets mixed and homogenized, is about 1,000 years. But an individual salt ion will spend about 50 million years in the ocean before it gets absorbed or brought down into the solid earth or whatever. So in its 50 million year lifetime in the ocean, it gets mixed many, many, many times. Every 1,000 years it gets mixed. So that's why everything is very, very homogeneous. So I made this with AI, I think it's pretty cute. And so basically this is the idea that this is a salt crystal, and he sort of explores the whole world ocean in his lifetime. Sees every little bit of it, probably many, many times on his expedition before he eventually leaves. And so based on this principle, you can actually infer, essentially by measuring how much chlorine is in the water, you can measure the rest of the salts based on a constant ratio. Okay, so I'm going to stop there. We'll finish this up next time. And I'll post the lectures, take a look at the assignment. If anyone has any questions, always feel free to reach out. And I will see everybody on, today's Wednesday, right? On Friday. Okay, all right, bye.